Key ideas in quantitative finance: correlation. So when we talk about correlation, we are talking about dependence. We're talking about how things are related. In fact, dependence is understood to be any statistical relationship between two random variables. Correlations refers to any of a broad class of statistical relationships involving dependence. Correlation usually refers to the extent to which two random variables have a linear relationship. So indeed, we could say that two things are related. This relationship could be of many times, could be linear, could be non-linear, could change in time, could be a function of time. It could be many things. But when we talk about correlation, the usual meaning of this term is the linear relationship between two random variables. There are good news and there are bad news. The good news is that there is a lot of theory about how this can be done. And a lot of it is due to Carl Pearson, who was a famous mathematician of the late 1800s and the beginning of the 1900s, that did a lot of great contributions to statistics, to mathematical statistics. He, amongst many other things, he contributed by inventing the method of moments, the p-value, the foundations of the statistical hypothesis testing theory, the chi-square test, principal component analysis, and he suggested the introduction of the histogram, and he invented also correlation coefficient. So he invented everything, fundamentally, in statistics. Not everything, but a lot of very, very important things. He was indeed a genius. We're looking today at the last one, the correlation coefficient. The correlation coefficient, which is indeed called the Pearson product moment correlation coefficient, is described here in this formula. It is obtained by dividing the covariance of the two variables that we are analyzing, capital X and capital Y, which are two random variables, and we are then using the product of their standard deviations, just as we see in the formula in here. By doing this, we have two time series that represent X and Y, which in practice could represent two prices of two time series of two stocks. And by doing the correlation, we can investigate if they move together or if they move in different ways, if they are not related. So this correlation coefficient will give us an idea if they both are reacting to changes in the financial markets in the same way, or there's no relationship between them, or in fact, if there's a negative value for the correlation coefficient, if they act in contrary ways. So when one goes up, the other one goes down. The application of this idea in practice is to take a set of values of n values, and just by calculating the R, that is the correlation coefficient of the population, then we can have an estimate of the correlation coefficient for the whole of the universe that these two variables describe. This is an example. Here we have a data set. We have variable x1 and variable y1, and this data set, after applying the correlation coefficient for this sample, we have that the correlation coefficient is 81.6%. This means that these two variables are strongly correlated. They move together, and this can be seen from the fact that when one goes up, the other one goes up. When one goes down, the other one goes down. In fact, we can fit a line that goes to most of the data, suggesting the relationship. At this point, there's the bad news. And the bad news is that we have what is called the Anscombe quartet. A statistician, F.J. Anscombe, published this paper, Graph in Statistical Analysis, in 1973, in which he gave a very important warning. And this warning said that most textbooks on statistical methods and most statistical computer programs pay too little attention to graphs. Few of us escape being indoctrinated with these notions. First, numerical calculations are exact, but graphs are rough. Second, for any particular kind of statistical data, there is just one set of calculations constituting a correct statistical analysis. Third, performing intricate calculations is virtuous, whereas actually looking at the data is cheating. A computer should make both calculations and graphs. Both sorts of outputs should be studied. Each will contribute to understanding. So Anscombe fundamentally says, don't look only at the numbers. Look also at the data, visually. And to convince us, he constructed these 4 data sets. And these 4 data sets are known as Anscombe's quartet. And these 4 data sets, which look very different, they all have the same correlation. If we compute the correlation coefficient for these 4 data sets, which are indeed different, as we can see from the graphs, we obtain the same value, 81% positive correlation coefficient. So this is the Anscombe warning and the Anscombe quartet, showing that in fact, when we want to analyze data, and in this particular case, when we want to analyze the correlation between 2 random variables, it's not enough to close our eyes and do the calculation. The critical thing is to look at the data and also, of course, do the calculation. Because the data, like in dataset 1, might be what we have in mind when we're doing the linear correlation coefficient, but we could have a nonlinear relationship, like in dataset 2, and compute a correlation coefficient that will not tell us a lot. Even worse in dataset 3, where we have an outlier and therefore the correlation coefficient, the same for all of them, for all datasets, could be meaning something very different, could be undervalued or exaggerated, as the case might be. And in dataset 4, well, no comment. What is the meaning of a correlation coefficient there?